What's my? I think number 13 and 14 is almost same problem. One just ask the formula, the other one just put the numbers in it, and they ask just find out the same answer. But the first one give that the number for some given parameters, but second one just ask drive formula. So we can maybe just take a look at this two question together. So for 13, there's my gosh. All right, let me change the color. So so number 13, the 15 meter uniform ladder weighing 500 Newton rests against the frictionless wall. The ladder makes a 60-degree angle with the horizontal. The number 8, define horizontal and the vertical forces the ground exert on the base of the ladder when 800 Newton firefighter has climbed 4 meters along the ladder from the bottom. So B, if ladder is just on the verge of slipping when the firefighter is 9 meters from the bottom, what is coefficient of static friction between the ladder and the ground? So now if I draw the picture, then it should be like this. You have the wall and the ladder leaning toward the wall, against the wall, and there's firefighter standing on the ladder. So that total length of this ladder is 15 meter. And I can tell you there's another problem with the exactly same condition later on. But if you solve this problem, you should be able to solve that problem too. So now the angle between the ladder and the ground is 60-degree, and the firefighter itself is 800 Newton, and the ladder itself also has weight, so that is 500 Newton. So basically, weight of firefighter is 800 pound, and ladder is 800 pound, and firefighter is 800 pound, and ladder is 800 pound, and the ladder is 500 Newton. And the firefighters sit on the ladder 4 meters above the ground. That is 4 meters along the ladder. So let's just quickly just take a look at this one. First step is just summing the forces in the horizontal direction, and the second you got to summing the forces in the vertical direction. So number one, you have to take a look at the forces in the horizontal axis. So if you think of this as x and the vertical axis is y, so there are two forces created by this firefighter on the ladder. So that if you take into account all the forces in the same direction, right? Forces in the horizontal direction. So your total force in horizontal direction should be 0. In order to stay this ladder in equilibrium, so all the forces based on the Newton's law should be completely balanced. So if you're summing the forces in the vertical direction, that is FB minus 2 weight, wall, ladder from the ladder, and the firefighter. So that should be also equal to 0. So net force should be equal to 0 out of the vertical force and the ladder and the firefighter. So now, as I said, you add two weights out of the ladder and the firefighter. So that's the ladder is 500 Newton. That is downward. And firefighter is 800 Newton. They also downward in vertical direction. So there is no horizontal component out of these two weights. So FH vertical force is 0 and FV minus 500 Newton minus 800 Newton equals 0. So that is same as F vertical force is 1300 pound. I mean, it's 1300 Newton. So that is forces created onto this system. Now with that idea, we gotta just figure out the frictional coefficient, static frictional coefficient, in the case that the ground on the surface of the ground is rough. So that create the frictional force, which actually hold this ladder from actually sliding. So in that case, force friction, the maximum is the frictional coefficient times normal force, which is mu s times F vertical. So, and also the torque exerted on this ladder is force of friction times lever arm, which is the force applied to this firefighter spot, produce that downward force, and also like the ladder itself produce downward force. So from that spot to the bottom spot right there should be the lever arm. So if you apply the frictional force on the surface, should be this direction. That is the force of friction. And if you multiply that length of the lever arm, which is this length, then that should be torque. So now if you plug that into this formula here, so basically your net torque should be equal to 0 too, in order to stay in equilibrium. So that is mu s times vertical force times lever arm d, which is our interest, and then you multiply the weight of ladder times 15 meter over 2, because we can assume that your center of mass sitting on the middle of the ladder. So your gravity, apply only drag that center of mass downward, and so that your effective radius of this torque should be 15 over 2, half of the ladder. And same time, firefighter times 15 minus 4, because the firefighter is just 15 meter, the 4 meter above this rotational center. So I'm sorry that yeah. So that's that's actually from this point to here is 15 minus 4, so 11 meter. If you apply that, then you solve this one, then that should be hold on. Okay, so that is I can't. You should move this one. So from that, your static frictional coefficient is 1 of F V D times this one is 500 Newton, and the weight of firefighters 800 Newton. If you plug that, that is 800 Newton times 15. Oh, sorry, the 500 Newton times 15 over 2 plus 800 Newton times 11 meter. And this one is 1300 Newton. And D is what? D is 9 meter. Is that right? I should be clear on that. Okay, so so if the B question B is just on the verge of sleeping when the firefighter is 9 meter from the bottom, so you gotta actually change this one from 15 minus 9, that should be 6. So we plug that into this formula, then that should be 1 of 13 Newton times 9 meter times 500 times 15 over 2 plus 800 times 6. Okay, that should be changed to the 6, 15 minus 9. So, do you have a calculator? Can you quickly
Yeah.
do some math to get the answer out of it? Does it look clear? If it doesn't, I can rewrite it for you.
Yeah, can you rewrite it one more time?
Okay, so here, frictional coefficient. Let me just take a lead of some of this. Hold on. All right. I can't. Oops. All right. So this one, oops, mu S should be 1 of vertical force times the lever arm times 500 Newton times 15 over 2 plus 800 Newton times 15 minus 9 meter. This is for B. Case A, the D was 4 meter, but now it changed the 9 meter. So this one is 1300 Newton. Right. So that should be 6 meter.
I got 0.73.
Okay, how much is it?
0.731.
7.73. Okay, that's it. All right. Let's move on. Any question?
I don't think so. No.
Okay, hold on a second. I think I need to change the volume of a speaker. Okay, the next one is on the one end of the uniform 4-meter long rod of weight Fg is, which is suspended by the cable, the angle of the 37-degree with the rod. The other end rests against the wall. Where is it held by the friction as shown in the figure 12.23? The coefficient of static friction between the wall and the rod is 0.5. Determine the minimum distance x from the point A If each an additional object also with the same weight, Fg, can be hung without causing the rod to slip at the point A. So in order to stay in equilibrium, the whatever force exerted on this rod downward should be same as the frictional force upward. So the two things you have to make sure the two forces should be in balanced, stay in balance, and also torque exerted on this spot should be same for the force out of the downward, the force downward, and also upward from the frictional force. So number 23, again. So now you have the wall and this rod, and that kind of like attached to the wall from the frictional force. And this cable support the rod, and the contact point between the end of the rod and this wall is only here. So that creates a frictional force. That frictional force support this rod itself as well as the weight or mass attached to the rod with the distance x from the wall. So you can imagine that the center of the mass of this rod is middle of this rod, right? So that should be total. If total length of this rod is L, and that is the angle of pivotal point of the cable to the end of this rod, and the center of mass supposed to sit on the middle of this rod, which is L over 2. And then weight of this rod Fg, and the other condition is this ball attached to this rod is also Fg, that in weight. So that is also Fg. So that's point A and point B. So the first of all, you look at the force exerted on this center of mass, and force downwards at Fg. So that is vertical force Fv, and that could be split into two vectorial component along that's this straight line of this cable. So if you plug that the angle into this relationship between the vertical force and the horizontal force, that should be Fb over Fh is tangent theta. So basically Fh is Fb over tangent theta. Okay, here, as I said, vertical force is Fg, gravitational force out of this rod. If you replace it, then horizontal force could be expressed with the vertical force Fg. So that should be Fg over tangent theta for the rod. And also the frictional actually torque. So the torque created by the friction on the point A should be expressed with the normal friction, the frictional force and lever arm out of this rod. So torque, frictional torque is the frictional force applied to the end of this rod times lever arm L, right? If you think of this one, B is the rotational axis, the center of the lever arm, that torque created by this force onto this point A should be expressed by this formula. Now, Fn is obviously that is vertical force and horizontal force. Horizontal force is, as I already just show you, the Fg over tangent theta. So if you replace it, the frictional force is frictional coefficient times Fg over tangent theta times L. That's the torque out of friction. So now, in the state balance, the two torques from the frictional force and the gravity of the ball should be in the balance. So that make the system in equilibrium. So torque from the friction to be same as the torque from ball. So here, the ball, if you think of B as the axis of the rotation, then that the torque which is created by this ball should be Fg times, hold on, L minus actually, L minus X times Fg. So this one and this one must be same to stay in balance. Now that's the consumption. So if you put them all together, then that should be mu S times Fg L over tangent theta equals L minus X times Fg. Because of the ball and the rod, they're same weight, that Fg are existing in both sides of this formula in torque. So that they can be cancelled out from this formula that lead to the single formula to express the frictional coefficient. So if you move L and tangent theta to the right hand side, that should be L over X over L tangent theta, which is 1 minus X over L tangent theta. Okay, so if angle is going bigger and bigger and bigger, then that you need less and less and less friction. So, I mean, more and more friction. And if you has this angle is smaller, then you have less frictional coefficient. Same thing for the variable x. If x is bigger and bigger and bigger, you have less friction because at close to the rotational axis, which need the less actually weight. So depending on the where that ball is located and which and how much angle you have with respect to this cable and this rod, and that this frictional coefficients also need to be the change. Okay. All right, that's the I think answer for this 23. Do you have any question?
No.
Okay, I think it makes sense.
Yeah.
All right. Oh, so 24, I think it is pretty similar. Well, hold on a second. Let me I will go over this one too, and then move on to next one. So this one is pretty much same, similar with the 20. I mean, actually 13, problem 13. That's why I mentioned that you will see that similar problem. So I'm gonna solve this problem in a similar way, like the number 13. So let's take a look. So you have a ladder, but instead of just the frictional force, the bottom of this wall is frictionally slippery. So if you don't have the force, horizontal force, obviously this rod doesn't matter how much weight you have on the ladder or how heavy the monkey is on the ladder, it always end up with the being sliding down to the and falling down to the ground. But instead of this frictional force, this rope play a role as the stopping force to support this rod that provide force horizontally and vertically that makes this ladder from the being dropping down, being dropped down. So we have to use the slightly different approach, but the whole idea to solve this problem is pretty much similar with the number 13. So let's take a look at the free body diagram, and we can actually just draw the picture of the force exerted on this system. So you have left number A, you have a ladder, and as I said, usually just the middle of this ladder is the center of mass, and that has gravity downwards, which is M ladder, and G, that is F G L, the gravitational force on the ladder. And you have a monkey, right, sitting on that the ladder that also have gravity downward, M G, which is F G M. And the bottom of this ladder attached to the loop, and that will be broken if you exert more than 80 Newton originally. So maximum force applicable to this ladder and this loop should be the tension should be less than 80 Newton. More than that, that's gonna just broken. The loop will be broken and the ladder will falling down. And the angle between the ladder and this ground is theta. So the same angle should be applicable to this monkey. So that weight, this should be theta, and this should be theta too. So basically, two force exerted on the downwards at the bottom of this ladder too. So that should be FGLM plus FGL2. So altogether on the bottom of this ladder. So that is number A. I put a free body diagram just with the the forces applied to this system. Okay, so now this is L, I think. So I draw the force diagram for the ladder, and number B, find the normal force exerted on the bottom of the ladder. So basically that is just F G M, the weight of monkey and the weight of ladder, times cosine theta is basically horizontal vertical force, and the normal force exerted on this surface of the ground should be combination of, as I said, the weight of monkey and weight of ladder. That is normal force. And B, and number C, we have to figure out the tension in the loop when the monkey is two-thirds of the way up the ladder. So the condition C now, number one, we have to first estimate the torque out of the tension. So here, the torque and the tension is this way, Ft. And if you think of this point, the top of this ladder is pivotal point A, then that's total radial component out of this should be theta, and that one actually. So basically this one is 180 degree minus a theta. Is that right? Okay, that's right. So that is LR, right? If you think of this one, A is the rotational center. So the torque is R LR cross products of vector of tension on the roof. So this one is L times FT sine 180 degree minus theta. So that is the torque out of the tension. And that's number one. Number two, we gotta just also estimate torque out of monkey. So that is L over 3, because the monkey stay the 2/3 of the ladder. That is the 1/3 from the point A. So that is L over 3 times weight of monkey times G, and the sine theta plus pi over 2 gravity. So that is this one, that gravity is downward, and same thing. So like rotational axis is just like point A. So that angle is that is 90 degree. That is downward, and this one is 90 degree. That theta m is 90 degree plus pi over 2. So that is the torque for the monkey. And now we got to estimate torque out of the ladder, which is the L over 2, because the center of mass sitting on the middle of the ladder. And now we have to multiply the ML, mass of the ladder, times sine, same thing, theta plus pi over 2. So basically net torque, total torque, should be combination of summation of torque from tension, torque from the monkey, with torque from the ladder. So if you look at the plus, then that should be minus L F T cosine. Oh, I'm sorry. This should be sine because it's 180 degree. So that is sine theta plus L theta m, the torque of the monkey is L over 3 mm g cosine theta, and plus L over 2 ml g cosine theta. So now that should be net torque itself also should be 0 in order to stay in equilibrium. The net torque is 0. So if you keep this formula to drive the your to find that actually tension in the lobe. So let me hold on a second. So yeah, let's move on. Okay, I'm gonna just maybe use the half of this one to solve that one. So basically net torque is the minus L ft sine theta plus L over 3 mg cosine theta plus L over 2 mlg cosine theta. That should be equal to 0. So if you rearrange this formula, that in terms of the ft, because that is what we have to find out. So tension ft is now it's LFT. If you move this one, the first term to the right hand side, that should be LFT sine theta equals LG cosine theta mass of the monkey divided by 3, and the mass of the ladder over 2. So now you see that the L existing in both sides of this formula, so that can be canceled out. So you divide the formula by the sine theta, the Ft. Tension could be expressed with the G cosine theta over sine theta times mass of the monkey divided by 3, and ladder of the mass of the ladder divided by 2. And this one is cotangent theta. That is the G cotangent theta mm over 3 plus the ml over 2. So that is tension on the rope to keep that system in balance. So now number D is find the maximum distance D that the monkey can climb up the ladder before the rope breaks. So maximum limit of a rope is 80 Newton. So if monkey produces more force than 80 Newton, then the rope would be broken and ladder will be falling down. So we have to find out the maximum limit of that. So in that case, so that the total torque from the rope is, as I said, minus LFT sine theta. And the monkey now, the location of the position of the monkey is parameterized with the D. So that is LM should be L minus D times the monkey's mass times G sine theta plus pi over 2. That is same as L over D mn G cosine theta, and the ladder same. The torque of ladder L over 2 mlg cosine theta. So just like the number C, net torque out of the tension, the monkey, and the ladder should be equal to 0. So net torque is delta T plus delta M plus delta L should be equal to 0. You plug them all, then that should be L Ft sine theta plus L minus D M Z cosine theta plus that should